We're ready to restart. So we've seen how loads were proposed to be able to respond to provide some frequency support or some even secondary response support. In Switzerland, for example, the company Tyco that does some control of heat pumps and boilers in houses, their business model is to provide secondary response support. So they provide to Swiss grid reduction or increase of consumption, and that's their source of revenue, which they get, and they get it by manipulating the user devices. Some people, in the context of a research project at IBM and in Denmark, had proposed even to go beyond and provide tertiary reserve. So remember, tertiary reserve is a long-term reserve that you expect to use only once in a while and has to hold on for some time. And here the idea is to use boilers. So here it's a bit more tricky. I mean, it's easy to stop a boiler for 5 minutes. Probably you will not notice much, except if the boiler is exactly down, and then you may have an escape mechanism that if the boiler temperature is really at the very low end, then it does not participate in this. And chances are, most boilers are not in this state. Here it's a more sophisticated thing, and the trick here is to look at cumulative curves, a bit like we do in network calculus, by looking at the total energy that is planned over time. So those are the curves that are given here. A boiler has a peak power that gives the max power at which it can increase its power consumption. And then to maintain its operation in a normal state, it uses, in average, some amount of power, which is given by the slope here, that is given there. But the trick here is, so this is the energy, this is the power curve for a given boiler here. The trick is to observe that there is a region of feasible operation for a boiler, which is, two extremal cases are, here you have a greedy boiler that is always trying to be as full as possible, full of energy. So this boiler starts, whenever it starts, it stores the maximum heat, and then we'll use, of course this will not be a straight line, but in average that will give this here, based on what users consume here. The other extreme is to do just-in-time production. You produce the energy exactly when it's needed. So you have no reserve, essentially, if you operate in this region here. And the idea of this proposal is to say that any trajectory that is within those two bounds is acceptable for a boiler here. If you violate the bounds, which means you are forced to go out, which is possible, for example, if the demand becomes larger than you had anticipated, or if you're not able to follow to heat as much as you would like here, then as long as you're inside the bounds, things are fine for consumers here. So their idea is to have a service aggregator that will choose middle trajectory for a set of boilers. So by analyzing boilers, so this is an IBM project, so it's a big data project. You take measurements on user behavior. From this, you can find, based on their average or their statistics of behavior, what are the two extremal trajectories, and anything in between that satisfies the peak power constraints is an acceptable trajectory. If you do that for one boiler, it's probably not interesting, but if you do that for millions of boilers over a country, then you can implement a reserve service by saying, for example, here is the trajectory. Remember, tertiary reserve is something that is expected to occur when there is a problem in the grid, so it will not happen every day, but when it does happen, you have to be ready to provide that service. So here the idea is, on a normal day, you work on this green line, and if there is a call by Swiss Grid for tertiary reserve events, Swiss Grid typically leaves you up to 15 minutes to react, so you have to be sure that after 15 minutes of that, you're able to provide the reserve service. What is the reserve service for a boiler? Well, it is to boil less, to consume less energy, which you're able to do if you're in that region. That region, in fact, tells you that the difference between the two lines, the vertical difference between two lines, is the storage that you have here. Here, that's the minimum stored energy you need. Here, that's the max that you can have. And if you're here, if you stop heating the boilers, then you can, which means you consume nothing, you're going on this trajectory. And of course, at some point, you will need boiling, but you can compute this, and they found that the duration that it has is in hours here. So take-home message, if you're able to aggregate millions of boilers, you can do even more than aggregating fridges. You can provide a service that is a bit smarter than Voltalis, that reacts instantaneously and in a greedy fashion. Here you can really control, because you have some storage here, and you have the information about the storage here. Those are all proposals. It's not, this form is not implemented. The future will tell if it can be implemented here. Something that has been tested on a small Danish island, although it looks close to Sweden, but I believe it's Danish, yeah? Bornholm, yes. So as an island is of course more sensitive to the power balance problem. They have one cable that goes to mainland, and this cable is limiting and is also often broken because the sea here is very shallow. So they had many, many experiences of blackouts, so people were very sensitive to that. So there has been a large-scale demand response trial there, and the major motivation here was really to match demand response with the volatility of wind. We can produce a lot of wind energy in this part of the world, but wind energy is very irregular, as you can imagine. And the thing that exists on this here is a coal plant that burns coal, imported from Poland or Germany, to provide services when there is a problem on the island. So a combination has been tried with demand response in homes, very classical things that combines all the things we've seen before. And the conclusion was that you could provide up to 3 megawatts of capacity in winter through demand response here. That's a very typical example where demand response is not able to solve the problem. Demand response plus wind energy will not run Bornholm, but you're able to reduce at least a capacity of 3 megawatts of coal plant here. You will need a bit more. You will need some form of storage. If you really want to run isolated on this island, you will need storage, batteries, like the big battery you can see in Mario Paolone's lab, this container. So that kind of batteries are the things that will need to be deployed if you really want to run it autonomously. But of course, if you do demand response, if you have 3 megawatts of capacity through demand response, the battery downstairs here is 1 megawatt here. So 3 megawatt is 3 batteries of this size here. So you will need batteries, but you will reduce the size of the batteries through such programs. A last example, which is not yet a problem, but will in the coming decades, many people anticipate it will becoming a very important problem, is the stress on the grid that is posed by charging electric cars. Here on the campus, we have electric car charging stations, but those are more or less toy things. We have thousands of parking slots and a few units of charging station here. Imagine in 10 years from now, if 20% of the cars used by people at EPFL are electric, and half of them wants to charge during the day. So we're talking of hundreds of cars charging on the grid of EPFL. For the grid of EPFL, already here it might be a problem if you want to charge them at the peak power. In many, many places of the world, the capacity of the distribution network will not be able to support charging of many, many electric cars. So you will need to do some grid reinforcement for the distribution network. which may be easy to do in some parts of the world, depending on the construction, depending whether there's spare capacity on a transformer. The only thing you need to do is to pull another line, and there is already a conduit in which you can pull the line. That's no problem. In places where the capacity is really at the limit, and you would really need to build another transformer or to add another line by digging holes in the street, that is, of course, extremely expensive. And it's not needed in many cases, will be needed for the base capacity, but you can mitigate and reduce the grid capacity that you need by doing what is called scheduling here. Scheduling is deciding when to schedule the cars. For example, this is how much you would charge on the grid. This is the voltage, that you will get on this grid when you have 30% penetration of electric cars. So showing a symptom, which is the voltage drop. But the voltage drop is just the first symptom that tells you that the grid is being saturated. How would you do scheduling? Where the idea is simply to say, if you charge overnight a car, and if everybody does it when they come home in the evening, there will be a peak problem, which is not a peak, might be a peak generation problem, but on this grid is simply a problem of the power flows on the grid, like we have seen in many examples before. So the power flows are excessive, but there is some flexibility. Most people do not need to have their car charged fully at exactly the evening. You just do it by convenience or because you ignore the fact that you could modulate it here. So if you could have an operator that is able to solve an optimization problem, then you can solve the optimization problem that consists in finding for every time slot, for example, a time slot may be 5 minutes or 15 minutes, what is the power you allocate to every car? And if you do this, then you can charge at a lower power such that you are able to satisfy the grid constraints. So that's exactly an OPF problem, perhaps combined with MPC if you have to have specific objectives for a charging station. So for more details, I think some of you are taking this project with the grid steer and Jagdish, who is also TA for this course. So he's starting a company that's interested in that, providing that kind of services. So those are, with all the techniques we have seen in the course, you can easily imagine how to do that. So the topic there was the distribution network itself. So we have two places where grids will be under stress in the future. The stochasticity of renewable energy poses a problem on the power balance that can be mitigated by reserves, but we can use demand response to reduce the amount of reserves. And the other thing is the grid overloading that may also be mitigated by demand response. And here typically the problem will come when there are electric cars. So this is a taxonomy of all the things we have seen. It's a very hot topic now in research. Like any hot topic, it will decay a bit. In particular, what some people are finding is that the revenue that you can obtain by manipulating thermal loads is very little. So companies like Voltalis, for example, have found that the best way to do it is not to pay to people a bit of money to reduce their power consumption, because it creates a lot of overhead in the amount you need to meter how much you give to everybody. So they don't do it. They just simply say, do it, we will get the money, you do it in order to be a good citizen, because you believe that with peak shaving we avoid burning more fuel that would generate CO2. So the economical model is an issue, but there are things to come in the development of dynamic systems for fridges, for electric cars, etc. So we can anticipate that this will come. So after this panorama and this very descriptive part, what we will go through is one very small theoretical which is the model under which all of those things are done. But before getting there, let me ask a question. Voltalis, as I said, has solved the economic problem that many demand response aggregators have, which is that if you want to charge millions of people, or you want to take accounting of millions of people to give them a few francs a month for the service they give, then the cost of doing all this accounting costs so much that there's no business model here. So they say, we don't pay for you. You allow somebody, a Voltalist, to come to your house, install a blue pod on your electric panel, and you do that because you want to be a good citizen. You don't want that France installs more nuclear plants or more diesel or gas burning stations. So you do that for the collective good here. And accidentally, they say, but you will also benefit by seeing a reduced electricity bill. You will consume less, a bit less. So we pay for this pod, we don't charge you for this, and your consumption will be a bit reduced here. Do you think that they cheat? Is this true, or is it pure marketing hype, or is there some scientific truth to it? If Voltalist comes to you, are you willing to say yes to them? So let's see what you guys think. So the majority thinks, A, yes, there must be a reduction in total energy consumed. Why? Why does anybody support this statement? Well, if they claim it, it must be true still. It's hard to do something large scale in a democratic country and be completely wrong, although Monsanto did it, but it needs considerable scientific sophistication to tweak the facts. So yes, there is probably some reduction in total energy. We'll come back to that in a minute. We'll see what the truth is and why. So before that, we'll do what is called the classical economical theory, which is behind a lot of the reasoning in electricity market. As you will see, it's a very naive theory, but that's the one that you must know because that's the one that's used. According to this classical economic theory, there are two things that you need to know. One is the utility. So you assume that users have some function which is measurable, and that measures what is the utility to consumer of consuming during a given period of time. For example, during the 6 to 7 period in the evening, you as a consumer will consume so many kilowatt hour during this 1 hour. What's the utility to you to consume this, right? And you assume that there is such a thing that you can formulate. It's a bit weird, right? None of us would know this function for us individually, but for, as we will see, for perhaps industrial consumers, that utility can be computed. For example, here I'm plotting Q on the x-axis, the power the energy that we consume during a given time slot, U, the utility. If you have a non-elastic load, for example, you come home and you want to switch on the TV consumes Q0, right? If you obtain Q0, if you don't obtain Q0, the value is 0 to you. If you obtain less than Q0, you want to switch on the TV, and you cannot because the grid is not able. In a hypothetical world of economists where the grid would be able to speak to you and say, yes, take this value or not. If you don't get what you need, then the value is 0 for you. If you get enough to run your TV, you have the value for you of watching TV, right? Which you can perhaps measure by how much you paid the TV and all that stuff here. If you get more, there's no value for you. The only thing you wanted to do was to watch TV. That's the curve you obtain if you have a non-elastic load here. If you have an elastic load, you probably have something like this. Elastic means you can adapt, so the more you get, the more happy you are. But probably there is what we see here, diminishing returns. This is not increasing faster and faster. Right? Is this concave or convex? Concave, yes. So the classical theory of economy assumes that utility functions are concave, here, diminishing returns. So you're more happy when you get more, but there is some saturation after some point when you have already a lot. Having the same delta doesn't have the same delta to the value as when you have very little here. And you might have an elastic load with a minimum requirement here. For example, you might be able to switch off some of the lights at home if somebody asks you to switch it off, or to reduce the temperature, change the temperature by 1 degree. There is a penalty for you, so there is less utility, but it's also not binary here. Right. Now, assume users react in this way. Again, that's the economical model. Whether users are this way or not, but that's what the classical economy thinks here. Not all economists are classical, but the classical ones tend to write things according to this theory. Now, you will pay the price of electricity. If a given time slot the price is P, what you will pay is P times Q. So the total utility to you is what you get, which you assume to be measured by this, minus what you pay. And if you're a rational user, you'll try to maximize this. This is trying to capture the fact that we're willing to pay more for some things, but only to some point, if that brings more value to us. This is assuming consumers are rational, right? Which other economists have shown is by far not true. And consumers react more to manipulations and perceptions, but this is what in this theory we can assume here. On the supply side, now, the supply side is much better understood, and here we're talking of big money and big companies. So there they have people that are doing accounting and financial planning, so they are rational here. Right? Now, assume you own a generator, and then you have a running cost. Of course, you have a capital cost, which we are not showing here. It's one of the issues of this theory. The capital costs are not easily explained by such theories, and the capital costs are one of the problems of the grid today. So we understand well how to run things day by day using this theory. We understand much less how to incentivize companies to invest in things that will be a 50-year investment, for example. Nobody has a career that lasts 50 years, so nobody is able to manage a 50-year investment. Nuclear plants, for example, are typically in Western Europe, or in Europe in general, invested by typically public money, because nobody wants to really invest in it using economical theory. So for the running cost, I assume if I produce an energy Q, I have to pay C of Q here. Then I will be able to sell, assume P is the market price, I will get my revenue, PQ minus C of Q here. The running costs are typically, well, either if your cost is, if you have a completely inflexible thing with zero or close to zero running costs, that's very typical of renewable energies. Right? For renewable energies, the cost is zero. Once you've installed it, it works or doesn't work. You have maintenance costs, but you have to pay the maintenance, whatever the energy that you deliver. And if you want to go above a certain value, the one that nature allows you to do at one point, the cost is infinite, because you cannot. Right? So that's the cost of renewable energy, the cost function. Fuel generators typically have a convex cost. If you want to, if they are well designed, that's not, sometimes they have an optimal operating point, but typically if you want to produce more, you need to burn more gas. That will cost you. And then if you want to push to very, very high amounts, then the cost becomes, is growing faster than linearly. This is very typical of all fuel-based systems, where the cost is often taken to be a simple quadratic function here. And of course, you may have also finite capacity, which means the cost becomes infinite to some point here. The economical theory often assumes that the cost is a function like this, which is here a convex function. Then the two curves that are used in the theory, in this economical theory, are called the demand curve and the supply curve. The demand curve is the derivative of the cost of the utility function. So it's the marginal utility of consumption. So it is saying, if I give you one small unit of consumption more, how much more happy are you? What's the delta? So it's the derivative du divided by dq, right? That's called the demand curve. So I'm plotting here the demand curve that corresponds to a hypothetical elastic load. If I have an elastic load, which has a concave function, if it's concave, its derivative is decreasing. So that's the typical demand curve. That's the derivative of the happiness or utility of customers here. And the dual of it, the supply curve, is the marginal cost of production, so is the derivative of the cost of production. If the cost is convex, then the derivative is increasing here, which is typically the case here. Now assume that you have a completely free market where price is set by the market, not by government or by long-term agreement, but by the market. Then the market will expose a price P. A given market has a price which is the same for all. That's the definition of a market. Now, if you're a consumer, an elastic consumer, you have a choice of how much you consume, your Q, and you will attempt to maximize your utility. If it becomes too expensive, you don't want it, but if it's cheap, you take it. So you maximize mathematically. This is captured by saying I maximize my utility minus cost here. If I maximize this at the optimal, so I'm assuming the price is dictated by the market or is an emerging property of the market. I am an individual consumer. I do not individually influence the market. One of the other assumptions that are here. Of course, in reality, in energy market, there are big players that influence the market. But if you don't influence it, you see the price Q as an externality, something given to you, the price P. So what value do you set to Q? The one that maximizes this. Now, that's an easier optimization problem than all the ones we've been confronted with in this course. What's the solution to that? The value of Q that maximizes this must be the one. It's concave minus linear, so it's a concave function. So the optimum is the maximum is the local maximum. You obtain it by taking the derivative equal to 0. U prime of Q must be equal to P. So if the price market is P, you will use Q given by that. Similarly, the suppliers will do the same thing. The suppliers will say, I'm willing to produce Q. The revenue I obtain is this. I maximize and I produce the Q such that the derivative is equal to P, which means that the market equilibrium will be at a point where the two derivatives are equal here. And therefore, we can summarize economy in one slide, which is saying you plot the demand curve, you plot the supply curve, and the market will stabilize at the intersection of the two. Which is simply saying that if users are elastic, if they're not willing to buy more, because if they take more, the price would be too expensive for them here. Right. So this is typically used. I mean, any literature you will read, any technical report, you will see that has to do with demand response will probably one of those curves here. This is, for example, showing what happens when we have a supply curve that is sharply convex, which is very typical. So you have production that you can increase at a fuel cost, which is modest here, up to the point where you have a hard time producing more and you need to use generators that are very expensive. And there is a limit here. There's an asymptote that you will not be able to go there. So this is the supply curve here. Now here, this is showing a demand curve. You see the demand curve is quasi-vertical, which means there is very little flexibility, which is very typical of what you have when there is no demand response here. And this is explaining why when the demand curve changes, for example, when the load goes from average to the peak loads, then we move here, and then the price of electricity becomes higher. And with this economic theory, the price is the marginal price of production. So the price of the market is the marginal price of production here, which is, of course, very good for all those who are producing here because they cash huge amounts of money when the demand is large. They have the same cost as before, but the market price is very high. So anybody that's running a business is trying to get to that nirvana where you can produce at very high revenue with low cost. And one way to do it is to go into that region here, which is when the demand curves becomes larger. Of course, another way is to move the supply curve down, which is what there was a scandal in California 10 years ago, where the major energy supplier of California was creating blackouts, so making the supply curve to the left in order to increase the prices here. That's one of the criticisms of control by price. If any actor that has a dominant position is able to manipulate the price, of course they will make the price very high because that's the signal that we need to control the system. And of course, when the prices are very high, they make a lot of money. So that might be pure manipulation here. Of course, elastic load might, if you have a load that is elastic here, then the curve will be very different. And instead of moving to this price here, you may move to a different price. This is also showing what happens when the supply curve has moved. As I said, when there's an outage or a manipulation, then of course the peak power may be extremely high, even though there is not much demand, much difference in the peak demand, simply a problem with the supply here, which is exactly what is happening now today. So the peak price of energy on the real-time market, once in a while, becomes extremely expensive, sometimes 1,000 times more expensive than the average price. And this is exactly because of what happens here. If the demand is inelastic, if everybody wants to live exactly the same way when the supply has dramatically decreased, then the price will become extremely expensive. And yes, this is showing what happens if you found a way to make your demand more flexible, of course, when you will hit this curve before the asymptote here. Okay, little quiz on decrypting supply and demand curve. Or here, demand curve, right? Here are three possible demand curves that you sometimes read in the literature. Which one do you think corresponds to the case that you have loads that have a very binary behavior? Right? Here I'm assuming that the loads are, I mean, some papers, Clement-Nyns paper, for example, are claiming that the demand curve is not a smooth concave curve, but people simply react by saying, now it's expensive, I stop it. They don't have a smooth reaction that say, I can fine-tune my consumption by saying, if the price goes from 5 cents to 20 cents, I will reduce my consumption by 12%. No, they say, oh, the price is high, now I stop. I stop means I don't heat my boiler, or I don't charge my car, or I don't wash my clothes. So if we do this, what is the resulting demand curve? And the majority says C, which is the correct answer. So if we look at here, so that's the typical, so the supply, the demand curve is the derivative of the price. No, that's the demand curve. What is it, the derivative? I guess, yes, that's the derivative here. So C means this third curve here. What happens when the price goes up here? If we follow the price here, then we see that there will be a jump in going from here to here. So there will be a sudden jump, a discontinuity in the consumption here. Exactly this point has been done in the Norway pilots that I mentioned at the very beginning. You remember I showed those price differentials between two regions of Norway due to the grid not being able to transfer all the power. And they claim with their experiment here, this price difference goes away if you just have people control their devices appropriately. Some other reports that I'm giving here for industrial customers are exactly showing the curves by saying how much people are willing to pay here for large customers. And they find some, of course, they don't find a nice curve, but they find plots that are with some strait of imagination, you can believe you could fit a line into this, and that could give you an idea of the demand curve for industrial customers at least. Industrial customers are probably well modeled by the economic theory, in the sense that if you go to a large industry like Monte or the chemical industry or very large electricity consumers, they can calculate exactly their costs and what is the benefit for them of responding to demand response event, for example, delaying the production of something or the consumption by 1 hour, 2 hours, 3 hours, if they know how much money they will get in return here. They will have a cost for delaying, they have operational costs for changing their production schedule. If that can be translated into money, that is something that is done here. However, so that's the major I would say, simple theory of demand response. But you have to know, because the one you will read, but of course you have to know its limitation. These limitations we have seen already. They're illustrated by this curve here. So the gray curve is the natural load, the one that you have if you look at today's system that do not implement demand response. And the red one is what you would hope to have if you do demand response. And perhaps what you get with economical theory. But in reality, what you will get might be something like this, right? There's a rebound effect afterwards. If your goal was to shave this peak and you have a larger peak after, perhaps that's good, perhaps that's what you wanted, because perhaps you're able to sustain this peak here, perhaps not. But certainly you should account for this. The economical theory doesn't do that. It's just, there's no time in it, or the one I presented. Perhaps if you want to do a PhD in the College of Management here with Daniel Kuhn on how to account for this, that would be an interesting topic. This has been done from an engineering viewpoint. Those are measurements, for example, obtained from the US experiments, showing what the normal load is in some, so those are, no, sorry, that's not, those are guidelines for operators of demand response in the US. And you should anticipate, for example, that after the demand response event, you have a higher consumption here. So if you call a demand response event as Romande Energie, you should not do it for this. You should do it if you're happy with that here, right? Which again might be a good thing to do. You might have a peak available generation here that you don't have now. For example, if this is over noon, over a sunny day, that's maybe something you want to do. This is captured by what is called elasticity. So I'll go quickly through that. We'll just give the reference here. So you can continue with the economical theory, at least for smooth curves here, and compute the elasticity, which is giving by how much, if you change the price, people will vary their consumption, but not just now, but if you vary the price at time t, what's the impact on the consumption at time t plus h, where h can be positive or negative. Right? That's the key thing that you have to do. Now, how you measure that, that's a bit miraculous and very approximate, but that has been done by doing some experiments on, for example, varying the prices and seeing how people react, and capturing the elasticity coefficient here, and some people have done it. For example, the reference I give, they found values that are small but important because you integrate all of those here. And you find that at the end of the day here, you have, for example, this thing here. So this is showing how the price is of electricity in a given region. If you do demand response, when there is a failure here. So that's classical demand response. It's not trying to adapt consumption to stochastic resources, but it's trying to adapt to breakdowns, failure, so loss of a big generator. So it's showing how the price goes when there is no demand response, and here this is how it goes when there is demand response. So we see we're not making exactly what the simple economical theory would be predicting, something flat. We do have fluctuations, but they are less than what we had before here. So take-home message, if you want to do demand response, you have to do an engineering approach to it. You have to model, you have to capture what will be user behavior. A very simple model is this one, to capture cross-elasticity coefficient. Other models exist. Some people criticize this by saying, but users are very binary. They don't react to price differences. They just react qualitatively to whether the price is high or not. So perhaps you would need saturating functions in this system, which is not given in this paper. And we're just at the beginning of analyzing this, and some of you will do it later. So let me skip that, I've mentioned that. The last thing I will cover very quickly is what is sometimes called evaporation. Evaporation is, by definition, so not to be confused with the rebound effect, it is the fraction of energy that is saved due to demand response here, right? So we see the energy is the integral of the curve. The gray one is what we have if we have no demand response. The pink one is what we have in reality. Of course, we've shifted the time component, but is it just a shift, or are we saving energy? Is Voltalis right when they say, if I do demand response on your devices, I will save energy, right? So is demand response saving energy? A priori, it seems weird. I mean, why would shifting things save energy? Normally, if you shift, I would expect the opposite. Why would I expect the opposite? For example, if I control the heating system of a big building, a campus, right? If I don't do demand response, so the price of electricity is fixed, what will you do for your heating system? You will do something, you will do a big optimization problem, like you know how to do now, and you will find what is the optimal from the viewpoint of your building, right? So you will minimize, you will be optimal in terms of, and if the price of energy is flat, you will have the minimum energy consumption here. Since that's the optimal you will have, any deviation from that, in particular if you follow a demand response program or if you follow the prices, might be at the expense of optimality. So if the optimality criterion was to minimize the price, the total energy consumption. Now, if you remember David's house we did last week, what were we minimizing? If we ignore the soft constraint due to temperature bounds, we're minimizing a weighted sum of the energy, sum of the PT, UT. If we do that, we're not minimizing the sum of the energy. So as soon as we manipulate things to be more efficient, we might consume more, because we consume more at a period where it's cheaper. Of course, socially it might be better, in particular if you have solar panels or reasons to believe that the energy done at this time is good energy that you can consume a bit more. But the question is, now are we really saving here? So is it true that demand response could save energy? So by definition, we call evaporation the difference, how much energy has disappeared by doing demand response. So E0 minus E1. E1 is assuming we obtain less. If the evaporation is negative, then demand response eventually consumes more energy. And my reasoning, qualitative reasoning, I said, if we're just optimizing, greedily building, doing demand response should produce negative energy, negative evaporation, because we're not truly optimizing. So let's translate that into a very concrete question. Assume in many years from now, you've been a very successful professional, you bought a chalet in the Alps, or you inherited from your parents because you're from valleys, and then the problem with the chalet is you go there not very often because you work hard here in the city. And what should you do when you're away, right? Should you interrupt the heating, or should you just heat when it's needed, right? What's your policy? So that's the question people often have, right? Should I keep my chalet warm during 2 weeks when I'm away for those 2 weeks? Or should I just heat it when I arrive? Or perhaps a bit before when I arrive. Of course, there are power limits. My heating system in the chalet doesn't have infinite power. So the temperature of the chalet is plus 5 degrees inside, and I want to come back in the evening, I will not be instantly able to move it from +5 degrees to +20. So I may need it to do in advance because of the ramping constraint. Also, I may need to heat my chalet to avoid freezing because the cost of repairing the water taps will be much larger than the energy saved, if there is energy saved. But on the other hand, heating the chalet when I come back consumes a lot of energy. So if you're a chalet owner, what would be your preferred policy? I close the poll, and we see that everybody says yes. So you will all close your heating when you're away because you're good consumers. Let's see the answer, right? We will go through the math of it with all the things we know. So first, I repeat here that, of course, when you come back to your chalet, you will heat more than if you close the heating, and when you come back, you heat more at this period where you heat. That's the rebound effect, right? You're doing demand response on your chalet heating system. But the question is not whether there will be more here, but whether the energy you've saved by not heating when you were away is offsetted by this one here. That's the thing here. We have the house model. Of course, this model can be criticized. It's too simple. It assumes a single homogeneous object that has a homogeneous temperature. In reality, it's much more heterogeneous, but still gives a first order approximation. Also, it's assuming there's no sunshine, which is probably not true in Valley. But if we look at those equations here, we can interpret them as simply the equations of a bucket of fluid where we put something into it, which is the heat, and as we put heat into it, the temperature, which is the level of the fluid here, so your thermometer is simply given here, and if you put more heat, then it raises here, but of course we also leak, we lose some of it here. So if we look at those equations, they are the same here. At least that's an analogy here. Now, if I look over a given period of time, if I have a certain temperature set point, T of t here, I integrate this here. This is the integral of energy I will use. This is the coefficient of efficiency. This is the total energy provided. And it will be equal to this, which is, this corresponds to the leakiness, how much I've leaked to the outside. And the inertia will tell us how much heat there is in the walls and in the objects of the chalet, which is the level of the fluid in the bucket. That's the inertia. Right? If the inertia is if the inertia is large, that means I have a very large bucket. I need to put a lot of fluid into it to increase the temperature here. Now I can compare two systems. I mean, the first system where I interrupt the heating when I'm away, and one where I don't interrupt the heating when I'm away here. So when I interrupt the heating, I have a certain building temperature. And when I don't interrupt, I will have an optimal building temperature, T star. And I'm assuming here we do that in the winter. When I interrupt the heating, the temperature will be less here. Now, if I look at what is the heat provided, it's given over a period of time, it's given by this integral. Now, how does this integral look like? K and C are positive coefficient. We see it's a function of the difference between the target temperature and the outside temperature. The initial temperature also plays a role here. But we see that it's a monotonic function of capital T. Right? If you set capital T larger, you will have the energy larger here, which is illustrated by this here. If you keep your chalet warm during the period you're away, you insist on having the temperature always at the target level. If you let it go down, you will do this, and when you come back, you will put much more heating there. But whoops, I've lost my channel. But all the heat I've put here is counted here, has gone out, or is in the bucket. Now, in the bucket, at the two, if I want comfort zone, if I have a system that has my good required temperature, is the same when I come back in both scenarios. What is the difference? The difference is how much I've leaked, right? Because all the heat I've put into it, which is the things I'm interested in, is either present in the bucket or has gone out through the leak, right? Now, the thing that goes out through the leak here, is less when the temperature is smaller, because the heat is depending on the temperature difference, right? When your chalet is warm, it leaks more temperature to the outside than when it's cold inside. If the temperature inside is the same as outside, the energy flow is zero. So some of the heat you produce here is used to keep the level constant, but some of it is used to go away more than here. This is why the energy is less here. So if you let your chalet cool down, you will benefit here. So what Voltalis said has been studied by the French Agency for Energy Savings, or for environmental and energy issues. So they've studied that, and they found, yes, it's true, that there was a lot of controversy about Voltalis. EDF has sued Voltalis because they put some perturbation into their revenue model. So this has been analyzed and scrutinized in detail, and they found that yes, we do save 10% on heating. So Voltalis received a lot of political support because it is reducing the energy consumption plus providing peak shaving. So that's wonderful for the grid and for ecology. They found, so some people in the agency studied that in detail. They found, yes, we do save 10% on heating. Voltalis works on heating and on boilers, but on boiler, there is no saving. Why do you think this is happening? And the majority, which is the single response, is number 2 here. That's the only plausible answer. House leakage is not negligible. Boilers are typically very well insulated because they are made, first, it's easy to do, and second, they are made to store heat, so they're well insulated. So if the leakage is very small, by delaying, in fact, or anticipating, you have no impact on the energy. But for houses, you do. So Voltalis does allow you to save energy, but the reason it saves energy is because it reduces your temperature. Once in a while, it reduces the temperature in the house. You would have the same saving by simply reducing the temperature always, right? So you would save this and even more, but this is what is happening. Voila. Thank you for your patience for the overflow in time. This is all we will do for today. So what we have seen today is the easier parts of demand responses. So now we're picking the fruit of all the hard work we've done over the past weeks and months. Modeling the grid is the hard part. Optimization is the harder part. And once we have all that, then the future is yours. You will be able to apply all this to all those wonderful projects that will come out in the future. And you're well equipped with that. And also hopefully well equipped for our next meeting, which is on Friday, for the last test of the semester on demand response, or MPC mostly. Right. Marguerite has prepared a small training homework, paper and pencil exercise to help you with the test. Last year the tests were quiz, you just tick a box. This year we think it's a better challenge to your intelligence to have you write things and just tick boxes. So in order to train you for how the test will look like, we have put something online for preparation for Friday. Voilà, thank you.